Okay, so let's start our class with the some ideas on how to use strain gauges for the stress and shear measurement. Now, remember, when we introduce the strain gauge, we notice that there is an influence of the transverse shear and the transverse strain into your longitudinal that we call natural measuring direction for the strain gauge. And for that, we define that the relative change of resistance, delta R over R, was set equal to this equation, okay, in which the KT was the transfer sensitivity of the strain gauge, defined as the ratio of Ky over K, where K is the strain gauge factor, the actual one, the longitudinal one, and Ky is the transverse strain gauge factor that is referring to the calibration material. Okay. Now let me introduce the x direction as the measuring one, the natural measuring direction for the strain gauge. So let me add this x here, okay, so that we can say that if we are having the x measuring direction is the strain gauge longitudinal direction. And of course, the y direction is a transverse one. And said that, let's assume that we are having a plane stress condition. Okay, if we are having that, the plane stress equation are leading us to write this relation between the strain, the axial strain, the transverse one, and the stress by this equation. And as well, epsilon y is 1 over e sigma y negative sigma x, in which x, sigma x and y are the stress, the normal stresses in the longitudinal direction for the strain gauge, and y is the transverse direction. Now, if we put this information into the expression that is giving us the relative change of resistance, then what we can say is that the relative change of resistance is given you by K over E sigma x negative sigma y plus KT K over E sigma y negative sigma x. That could be rewritten as K over E sigma x 1 negative KT plus K over E sigma y KT negative. Okay, so that is the general equation that is giving me the information of the relative change of the resistance when we are operating in a plane stress condition, and we are having a change of the resistance of the strain gauge because the strain gauge is attached to this bond to your hot structure. Now, because we would like to measure
I can actually hear you fine. I'm not sure if other
okay,
students can, but I can.
so can you hear me?
Sì, professore, c'è un po' di eco però, almeno io sento eco.
Ma non dipende da me, credo. Please mute your microphone. Maybe you can reduce the echo. Because I don't have here.
Yeah, there is an echo on your end.
Professore, i microfoni erano spenti prima, quindi mi sa che non dipende da chi sta seguendo.
Can you hear me now?
Sì.
Maybe it's you. Yeah, can you, maybe it could be there. Is there any echo? Yes, there is. I don't know.
Comunque non è niente di troppo fastidioso, cioè si sente...
Okay, can you follow, however, can you follow anywhere the class of all these echo? Okay. So now we are designing which one? The last line? Yes, that's what we had. Just put the piece of information on this relation. So you have to put epsilon x and epsilon y that I wrote there. Kt times k over e. Yeah. Write that in this way. Okay. Just a second. Okay. Now we are designing the strain gauge so that we can have information on the stress and shear. So what we can say is that if the strain gauge is designed so that we have Kt negative me equal to 0, then what we are having is that the change of the resistance, the relative change of the resistance, is equal to K1 negative me square over E times sigma x. And thus we have found out a way of measuring the stress in your test specimen under the assumption that it is working under the plane stress condition. And this relation is a linear one, so we like it very much because I can define this coefficient as K, for example, K sigma. So K sigma is defined as K1 negative me square over E, so that we have the final relation is that the change of the relative resistance is equal to this K sigma times sigma x. And that is a very nice relation once again. Okay. However, we are not having this information, this formula, this approach in estimating the stress, measuring the stress using the strain gauge, because it is better to use a different configuration that makes use of two strain gauges, okay, instead of one that we are considering just. Okay, so this configuration that allow us to measure the stress using two strain gauges is called the V configuration. So now I'm going to tell you. So generally, stress is measured using two strain gauge, and that is called the V configuration. So strain gauges in a V configuration. What does it mean? That it means that we are having one strain gauge, for example, here, another one there, so that the measuring directions are the one or the longitudinal one for each strain gauge. Let's assume that these strain gauges are located in a reference frame like this. So X and Y are the given reference frame, so that the two strain gauges could be identified in the given reference frame from the angles theta assumed to be equal, okay, in amplitude. Let me call strain gauge, the upper strain gauge, as A and the lower one as B. Oh. Ma io sto facendo lezione adesso, è un problema? Alle 4. Se fate silenzio e siete invisibili va bene, e non parlate perché altrimenti già c'è un eco. Okay, so if you are using two strain gauges in that reference frame and you locate those strain gauges with an angle theta and positive theta and negative theta like that, we can rewrite the very well-known equation that allow us to have the expression of one strain in a given reference frame into another one, just by writing, for example, epsilon A, that is the strain with respect to the x-axis plus the angle theta, okay, that is equal to epsilon x cosine square theta plus epsilon y sine square theta, and the shear epsilon xy sine theta cosine theta. We can rewrite the same thing for the strain gauge B. Epsilon B is equal to x negative theta, and so epsilon x cosine square theta plus epsilon y sine square theta. Okay, and then negative epsilon xy sine theta cosine theta. Once again, these are the strain in the measured by the strain gauge A and B, that is in the two directions theta plus theta and negative theta, expressed in terms of the strain in the XY reference frame. Now, let's see together. Our task is find out a useful formula to have the stress and the strain, okay? The stress basically. So let's find out what happens if we add these two strain gauge measurements, so epsilon A and epsilon B. So let's see if we add epsilon A and epsilon B, what comes out from our equation. That is, let us sum x plus theta and x negative theta. If we put the things together, we say that this is equal to twice the sum that is 2 cosine square theta epsilon x plus cosine square theta epsilon y. Okay, just makes an algebra. Because we are designing such a measuring device so that we can have information concerning the stress, let's assume that the orientation angle theta and the Poisson ratio are related by this equation. Or if you want, I am choosing the theta angle so that tangent square theta is equal to the Poisson ratio, or positive. Okay. If that is true, then we can say that the cosine square of the angle theta is just equal to 1 over plus Poisson ratio, like that. Okay. And thus, what is the sum of the two measurements, epsilon A and epsilon B, is equal to 1 plus me epsilon x plus me epsilon y. Once again, if we are in a plane stress operating condition, then it happens that this normal stress is equal to this equation. Okay. Now, we are almost there. Just put the previous equation into this plane stress equation, and what we got is that sigma xx, the normal stress, is equal to E over 2 1 negative me, and then epsilon A plus epsilon B. And that is your final equation. Because generally, the sum epsilon A plus epsilon B is given from the Wheatstone bridge configuration measurement. Okay, you can have that straight from the measuring device that you got, for the bridge device that you got. So you can know from the measurement, you directly know from the measurement the sum of the strain, and thus you have the information of the stress. Okay, because what you have to do is just the information of the calibrating material, or the material, that is E and the Poisson ratio. Okay, so from the measuring device, you know the sum of the two measurements, or the half of the sum, depends on the configuration. Okay, then if you know the Young modulus and the Poisson modulus of the material, then sigma is known from the previous equation. Okay. By the way, saying that tangent square of the angle theta is equal to the Poisson ratio, if we are assuming that the Poisson ratio is about 0.3, okay, that means that your theta angle is 30 degrees. That is a quite feasible condition. So that you have to find out a material having the Poisson ratio of about 0.3, so most of the metal alloy that we can have, light alloys or metal alloys, whatever. And then you have to use two strain gauges, go to the very top here, so that the theta angle is equal to 30 degrees. Okay, once you have that, just the measurement of the sum or half of the sum of the strain that is related to straight to the, what is it? Yeah, to the stress using this ball. Okay. A different way of using the V configuration, the strain gauge V configuration, is coming out from the evaluation of the difference of the two measurements. So instead of evaluating the sum of epsilon A and B, that is the sum of the two strain gauge measurements, let's have the difference. So okay, so from such a difference is equal to epsilon x cosine square theta A negative cosine square theta B plus epsilon y sin square theta A negative sin square theta B plus epsilon xy sin theta A cosine theta B sorry, negative sine theta B cosine theta. Now if you rewrite this term as 1 negative cosine square theta A and this other term as 1 negative cosine square theta B, okay, then you can have the difference between the two strain gauge measurements, okay, rewritten as epsilon x negative epsilon y cosine square theta A negative cosine square theta B plus epsilon xy and theta A cosine theta A negative theta B cosine theta B. Okay. Now we are once again designing the strain gauge. So let's assume that we change or we set the orientation angle between these two strain gauges so that the cosine squared theta A is equal to the cosine squared theta B. Okay, or that is the same cosine 2 theta A equal to cosine 2 theta B. Okay, so if that is true, we have that the difference between the strain gauge measurement is equal to 1/2 epsilon xy sine 2 theta A negative sine 2 theta B. Okay. And so your epsilon xy is equal to 2 over sine 2 theta A negative sine 2 theta B epsilon A negative epsilon B. And if we define this term that depends just on the orientation of the two strain gauges, and we name that as the sensitivity KXY 2 over sine 2 theta A negative sine 2 theta B. Okay, we can rewrite that equation just writing xy equal to kxy epsilon A negative epsilon B. Okay, now please consider that if the statement that is cosine square theta A is equal to cosine square theta B, that I will write that here. Okay, so if cosine square theta A is equal to cosine square theta B, that means that theta A is equal to negative theta B. Okay. Of course, there should be also another option. Theta A is equal to theta B, but that is with no interest. Okay, because we are just having two strain gauges overlapped over the other, so it's not the thing that we are looking for. So if we are having theta A equal to negative theta B, and if theta A is equal to pi 4, what we got is that the shear strain is just epsilon A negative epsilon B. It is much more interesting. Okay. Please note that if you're using the Wheatstone bridge and you are connecting strain gauge A and 4 and B to Wheatstone bridge leg 1 and 4, then you have the reading that is just the shear strain, because this Wheatstone bridge is giving you just the difference between these two strains. Okay, so the shear strain if you touch these two, yes, the reading is epsilon xy, but you have to have that the orientation angle is pi 4, okay, 45 degrees, and these two must have a 90-degree orientation, so negative and plus. Okay, so the shear strain, as a consequence, we can say that could be measured direct from the Wheatstone bridge. If the strain gauge are oriented in a plus minus 45 degrees configuration. Okay. And strain gauge A and strain gauge B are in legs number 1 and number 4. Okay. Generally, what we are having also is that in order to increase the sensitivity of the strain gauge, we can use 4 strain gauges, okay, in order to increase sensitivity. But
What does it say
the-
after you have if the strain gauge and what's the word after? I think and.
and strain gauge B. So we got 2 strain gauges, strain gauge A
No,
and,
so
and strain gauge B
right.
are in leg 1 and 4 of the Wisdom bridge.
So above that you have if the strain gauge.
Okay.
No, not that. Above that, you at the start of that sentence, you have if the strain gauge and what's the word after and? Above that. No. Above that. No, not strain gauge A.
This one?
No, yeah, no, above it.
Above it?
Yeah, get it closer.
Strain gauge, SG.
Okay, yeah, so can you read that sentence? If the strain gauge and something
are oriented.
Got it.
Are oriented.
Thank
Okay.
you.
In a plus minus 45 degrees. This is a consequence. That is, if you are having from the analytical point of view cosine squared theta A equal to cosine squared theta B, then that equation simplifies into the one that they wrote. Okay. From the geometrical point of view, that is from the configuration point of view, what does it mean there? It means that you should have these 2 angles that are equal opposite in direction. Okay, so theta A equal to negative theta B. Moreover, if these angles, that is just one angle at the very end, is 45 degrees, you can even simplify the kxy as I call it. Okay, and in that case, it is just equal to 2. So you can simplify, and therefore the epsilon xy, the shear strain, is just the difference of the 2 strain gauge measurements. Because it simplifies even more. We are interested in that, because if that is true, you can use the Wisdom bridge, and the output of the half bridge configuration is telling you straight what is the shear strain gauge. The shear strain. Okay. It's different way. Okay. Other questions on that?
Yes, Professor. The 45-degree orientation is with respect to principal strain, right? The position of the strain gauge, or it is
not principal, not at all. With respect to the reference direction, which you are evaluating epsilon xy. The idea.
Okay, but normally we have a 45-degree apart from the principal strain. You get shear strain, right? In normal representation.
You don't know where the principal direction is located.
Okay.
So what we are doing is just, if you bond your strain gauge B configuration so that you would like to know the shear strain in the point that is the origin of your whatever reference frame like that, then if those conditions are satisfied, then you have that the Wisdom bridge measurement from leg A and 4 is giving you information of the shear strain. And for that, you can have also the shear stress just by multiplying that by the shear modulus. Okay. So what you got here is a very nice relation that is telling you what happening, or how can you measure the stress, normal stress, okay, using just one strain gauge, okay, the first part of this representation. Then you can use a B-strain configuration, and therefore you can have a call just to be sure about the orientation angles. You can have a very easy way of estimating, of measuring the shear strain, okay, and therefore the shear stress. Mhm. Where is it? Where is it? Where is it? So funny. Here? The Poisson ratio is the ratio between longitudinal and transversal strain. But however, you can see that just from the analytical point of view. If in that equation you have that tangent square theta is equal to the Poisson ratio, that equation simplifies. It is a simplification right now. Okay? And therefore you can say that you have this very nice equation. Now, what does it mean from practical point of view, that assumption? Here we go. That assumption means that you should have theta equal to 30 degrees. Okay, one each other. Okay, you are designing that, and if theta is equal to 30 degrees, then you can have a very easy expression. Doesn't matter. It is a simplification. Everything comes out. Okay, because where is it? Here. If you're saying that, then everything stay here. Of course, you can't do anything about the material. It is just a change of orientation between these strain gauges. Okay. Remember, you are having this configuration that is two strain gauges A, B that are oriented in whatever way. Okay. Depends on what you want to do. Okay. If you want to have the stress, normal stress, we proved that you get this very nice equation. Where is it? Here. Okay, here. Okay, in which you are assuming that there is tangent square theta equal to Poisson ratio. That is theta equal to 30 degrees. And then you got that very nice equation. If not, you have to come back here and see what happens. Okay, it's not that easy. Okay. Then, how about the shear stress and then shear strain? We compute the difference instead the sum of the two strain gauge measurements, epsilon A and epsilon B, and we found out another property. If we set the V configuration so that the two strain gauges are 45 degrees apart, then the shear strain is very easy, just the difference between epsilon A and epsilon B. And that is much more interesting because it is the output from the Wheatstone bridge. So you don't have to do anything else. epsilon 1, epsilon A negative epsilon B if they are set in a the first and fourth strain gauge length. Okay. Okay, let's have 5 minutes break and then we can recap the rest of the class. E quindi vanno a doppio, 2 volte. O vanno con le stesse orientazioni